Example 10. For the reservoirs marked with A, B, C, and D on the table, determine the flow rate in or out of the reservoirs in liters per second. So we are given here the roughness coefficients, different roughness coefficients. So to help analyze the situation, let's draw the figure and the elevations. The pipe characteristics are in the table. So first is we assume no flow in or out at B, so that we can compute partial discharge in 1 prime. So head loss is 15. 120 minus 105 is 15. Imagine isometric level here, or energy level here. So 15 equals 10.29 n 0.01 square, length 1800, discharge 1 prime square, over diameter to the 16 thirds. Remember the formula by Mannings. So Q1 prime is equal to 0.1148 cubic meter per second. And we're supposed to compare it with Q3 prime and Q4 prime. So we'll just compute Q4 prime. Anyway, if Q4 prime is greater than Q1 prime, then there's no need to compute Q3 prime. It is already, Q1 prime will be already less than Q4 prime. So 45, 105 minus 60 is 10.29, 0.013 square, length 1000, Q4 prime square over diameter 0.4 to the 16 thirds. So Q4 prime is 0.4419 cubic meter per second. So therefore, Q1 prime is less than Q3 prime plus Q4 prime, because even Q4 prime alone is already greater than Q1 prime. So that means the isometric level is maybe between B and C. And because the elevation between C and D is 20, the difference, so there's a possibility that the isometric level will be above C. So the discharge equation will be Q1 plus Q2 equals Q3 plus Q4. So let's try that. So that's the flow direction. And this is the isometric level. We'll call the head loss in pipe 1 as H. So this is H minus 15, HF2. Then HF3, this one is, the difference is 40, so 40 minus H, HF3. Then 120 minus 60 is 60, so this is HF4, 60 minus H. So discharge formula Q1 plus Q2 equals Q3 plus Q4, where Q from this equation here is head loss diameter to the square root of head loss diameter to the 16 thirds over quantity 10.29 n square length. So this is the formula. And as I said, there's no need to compare Q1 double prime plus Q2 double prime with Q4 double prime when there is no flow in or out to reservoir C, because we anticipated that Q1 plus Q2 must be equal to Q3 plus Q4, hoping that's the case. If not, then we cannot find a value of H which will satisfy the equation Q1 plus Q2 equals Q3 plus Q4. So it should be Q1 plus Q2 plus Q3 equals Q4 if we cannot find H. So square root of H, 0.3 for pipe 1 to the 16 thirds over 10.29.01 square, length 1600, plus Q2. Q2 is quantity, square root of quantity H minus 15. Diameter is 0.25 to the 16 thirds over 10.29 times 0.011 square. Then the length is 900. Then equals square root of quantity 40 minus H, 0.2 to the 16 thirds over 10.29, 0.012 square, 1500, plus square root of 60 minus H times 0.4 to the 16 thirds over 10.29, 0.013 square, then 1000. So simplifying the radical, we have 0.02964 square root of H plus 0.023 43 square root of h minus 15 equals 0.009176 square root of 40 minus h plus 0.06587 square root of 60 minus h. So only h is the unknown here. By trial and error, if you're not allowed to use high-tech calculator, so you'll find h should be between 15 to 40. That's the range. So make sure that the left is equal to the right. So solving for h is 39.63 meters. So we can now compute Q1. Q1 is 0.02964 square root of 39.63 times 1000 to convert it to liters per second. That's the requirement in liters per second, 186.6 liters per second, and it is an outflow. Q2 is also out of reservoir B. So this is Q2 0.02343 square root of 39.63 minus 15 times 1000. So Q2 is also outflow 116.3 out of reservoir B. Q3 is 0.009176 square root of 40 minus 39.63. So it's just above elevation C, the isometric level. And it is equal to inflow to reservoir C, 5.582 liters per second inflow. Finally, this is Q4, 0.06587 square root of 60 minus 39.63 times 1000. So Q4 equals 297.3 liters per second, and it is also inflow to reservoir D. So that's it for this problem.